So suppose you take the SAT test and the ACT, not using the chart on the College Board. Can you directly compare the SAT math with your ACT math? So if you scored 700 on the SAT math, and then you scored, I don't know, what's a score on the ACT math? Like 20 or something. Can you say that you did better on SAT because you got a higher score? Does that make sense? Because I got 700 points versus 20 points, I did better on the SAT. Does that even make sense? No. So they are scored differently, so you would say no. They're scored differently. They're on a different scale, and they're different proportions. So it doesn't make sense to say I got more points on the SAT than I did on the ACT, because they're scored differently. They have different proportions. So we call that a standardized score, which is also known as a Z-score. And so what a Z-score is, it means relative to that particular test, relative to that proportion, I scored better or I scored higher on the ACT than I did the SAT, because relative to that test. So you're comparing it within the test. And so everyone in here has taken the SAT or ACT, I hope, by now. And all of you got a score. You also got a percentile. And that was based off of everyone else that you took the test with. So if you scored in the 80th percentile, that means you did 80% better than everyone else. And that is also a standardized score, or a Z-score. So Z-scores are standardized. That just means it's relative to everyone else, relative to everyone that took the test that day. It tells you how many standard deviations the original value is from the mean. So that's kind of the definition that I want you to know what a Z-score is. How many standard deviations from the mean? A distribution of Z-scores has a mean of 0 and a standard deviation of 1. So the formula that I want you to memorize is Z equals, so Z represents your Z-score, X minus mu over sigma. And so what that means, it's your X value, like what you scored on the test, minus the average, minus the mean, divided by the standard deviation. So that's kind of what it means in general terms. So you take your X value, like you scored a 95 on the test, the average was a 90, and then the standard deviation was 2. So you would take your X value minus the mean over the standard deviation.
When is this test?
I just said that.
I just asked.
It's in 2 classes. So here's an example. It gives us an average of 50 and a standard deviation of 5. And so if the X value is 55, what is the Z-score? So I'm going to plug that into the formula. I would take my X value, which is 55, minus the mean, which is 50, all over 5, which is the standard deviation. So 5 over 5, that reduces to 1. So that means that I am 1 standard deviation above the mean. I'm above average. For the second one, if I made a 45, it would be the same process. So 45 minus 50 over 5 gives me a Z-score of -1. So that means that I am below the mean. I am below average. So if you have a negative Z-score, you're below the average. If you have a positive Z-score, then you are above the average. So 10 over 5 reduces to 2. So that means I am 2 standard deviations above the mean. So what does the Z-score tell you? The formal definition is how many standard deviations above or below the mean. So if I had a Z-score of -2.3, that would mean that I am 2.3 standard deviations below because it's negative, the mean. And then a positive 1.8 would be 1.8 standard deviations. I'm just going to abbreviate that to be SD. Above the mean. .1 below, or above, sorry, it's positive, above, and then 4.3 below. So we have an example. It says Jonathan wants to work at Utopia landfill. He must take a test to see if he is qualified. So the test has a normal distribution, so that means that I can use the z-score formula. It has a mean of 45 and a standard deviation of 3.6. So what I normally do is I write it out to the side just so that I either highlight it or I write it out to the side. And then to qualify, he cannot score lower than 2.5 below the mean. So I need to find his z-score and see if he did better or worse than 2.5 standard deviations. He scored a 35 on the test. So to find his z-score, I would take 35 minus 45 and divide by 3.6. So if you type that in your calculator, you end up getting negative 2.78. So does that mean that he qualifies for the job or no? Like, did he do better or worse than 2.5? He did worse. So if you think about putting it on a curve, here's negative 2.5. Negative 2.78 is further away from the mean because it's a further distance. So no, he does not qualify. His test was too low. Okay, number 5, it says Sally's taking 2 different math achievement tests. So test A has an average of 56 and a standard deviation of 3.5, so that's test A. And test B has an average of 65 and a standard deviation of 2.8. So I have 2 tests, A and B. Sally scored a 62 on test A, so her score on test A is a 62 and a 69 on B. So you can't just look at it and say, oh, she got a 69 on B and she did better, because it's all relative to the averages on the test. So it's like taking Unit 1 and Unit 2 tests. Maybe you scored higher on Unit 2, but everyone did terrible on Unit 1, so you really did better on Unit 1 compared to everybody else. So I need to find her z-score for A and B. So to find the z-score, I take her score, which is 62, minus the average over the standard deviation. So her z-score on test A is what? .71. Let's go out 2 decimal places. And then her score on test 2 is 69 minus 65 over 2.8. You should get 1.42. So which test did she do better on, A or B? A, because of a higher z-score. So a higher z-score means a better grade. So a density curve is kind of a form of a normal curve, but it's basically a continuous graph. It is continuous. So it gives you a range of values. The area under the curve is what we're going to find. So all that I really want you to know from this, that it has an area of exactly 1 underneath. That's mainly what I want you to get from a density curve. It has an area of 1. So if I added the area under the curve, if I calculated that, any of you in calculus will start talking about that with integrals, but if you're finding the area under the curve, the whole thing adds up to 100%. And we use that to calculate probability, the chance of something happening, how often something is going to happen. So a normal curve, which is like this pillow right here, this represents a normal distribution. So any test that you take, like the SAT, the ACT, any achievement test, is put onto a normal curve. So every single one of you has a score on this normal curve, and that's how they do bell curves. That's how they standardize any of your scores of things that you take, because every single person has an individual place, and it helps you calculate percentiles, the percentage of who scored above what. And in a normal curve, it is always bell-shaped. So it always looks exactly like these pictures right here. It is centered at the mean. So the center is always your mean. And then it goes out standard deviations on each side. So we're going to have some practice drawing that. But essentially an entire normal curve is within 3 standard deviations on each side. So I'm adding a standard deviation, adding standard deviation, adding, subtracting, subtracting, subtracting. As your standard deviation increases, so let's say you have a really big standard deviation. If you have a big standard deviation, your curve gets wider. If you have a small standard deviation, so it decreases, then you have a really tall and skinny curve. Okay, so it's kind of the same thing with any distribution you've seen. It's really condensed if you have a small standard deviation, and it's really wide if you have a big standard deviation. The empirical rule, the only 3 numbers that I want you to get from this is if you are centered at the mean, so here is my mean right here in the middle of the normal curve. If you go out 1 standard deviation on each side, so let's say that my average is on the test was an 80, and then my standard deviation was 3 points. That means that if I add a standard deviation, so 83, and I subtract 1, 77, so I added 3 and I subtracted 3, that means that 68% of everyone in my population, everyone in this class, scored between a 77 and an 83. So 1 standard deviation away is 68%. If I go out 2 standard deviations, so 74, 86, 95% score within 2 standard deviations. And then the last number is 3 standard deviations, so 71, 89. And I'm getting these numbers by adding 3, adding 3, adding 3, subtracting 3, subtracting 3, subtracting 3, because that's what my standard deviation is. So if I go out 3 standard deviations on each side, 99.7% of you scored within a 71 and an 89. So the 3 numbers that you have to memorize just from this slide are 68, 95, 99.7. So 68 is within 1 standard deviation from the mean, positive and negative. 95 is within 2, and then 68 is within 3. Or 99.7 is within 3. So basically the entire population, 99.7% of them, score within 3 standard deviations. So the calculator will calculate the standard deviation in such a way that fits this model right here of 68, 95, 99.7. So 68% are within 45 and 55, 1 standard deviation. 95 are within 40 and 60, 99.7 are within 35 and 65. So in an example like this, you can use your calculator to calculate the proportions or the percentages underneath the curve. So here's an example. It says the height of male students is approximately normally distributed. So I have a normal curve. It gives me a mean of 71 and a standard deviation of 2.5. So if I have my normal curve, my mean is 71, then I have a standard deviation of 2.5. So question A says, what percent of male students are shorter than 66? So here's 66, and I want to find the percentage shorter than that. I could use the empirical rule meaning I'm going to go down 2 standard deviations and then find the area to the left of that. But I'm going to show you how to use your calculator because it's a lot easier. So when you go to your calculator, you're just at the home screen or whatever. You're going to hit second VARS, hit the VARS button. And then I want you to choose option number 2, which is normal CDF. So I have normal CDF. You're going to have, does everyone have a menu that prompts them to do a lower and an upper bound? Yes. Okay, if you have an Inspire, you're going to hit menu 552. If you have an Inspire, menu 552. If yours doesn't have something to prompt you the lower and upper bound, then you need to update the calculator, and I will do that for you. So normal CDF, it gives you a lower, an upper, a mean, and a standard deviation. So when you're thinking of this normal curve, lower and upper is kind of like your domain, like from left to right. So my shaded area right here is everything from negative infinity all the way to 66. So my upper bound would be 66. And I need to type in, this is negative infinity. So in order to represent negative infinity on the calculator, I just choose, I say negative 2 to the 99th power. So for my lower bound, I'm going to type in negative 2 and then the little up button to the 99th. So negative 2, 99th. My upper bound is 66. So this contains the area from negative infinity to 66. My mean, it gives me, so 71. And then my standard deviation is 2.5. So lower bound should say negative infinity. So you should get negative 2 to the 99th. My upper bound is 66. My mean is 71. My standard deviation is 2.5. Then you hit enter, you get 0.0228. So lower bound is like the left. Upper bound is what is to the right. So I'm including everything from negative infinity to 66. My mean is 71. My standard deviation is 2.5. So when you're answering a question like this on a test or something, I want you to write out what you type in the calculator and your answer. So your answer would look something like this. And this kind of thing just takes some practice. So let's try the next one. It says taller than 73.5. So my 73.5 is going to go over here to the right of my mean. And then I want taller than that, so I want to shade the area that is greater than 73.5. So I'm going to go to normal CDF. So second VARS. My lower bound now is what? If I'm reading it from left to right. 73.5. And my upper bound, I'm going to shade forever to the right, so it's going to be what? Positive infinity. The way to represent positive infinity in your calculator is 2 to the 99th power. Because that gives you a really, really, really big number, which is approaching infinity. So that's positive infinity. My mean is still 71, and my standard deviation is 2.5. So hit enter. You should get 0.1587.